This conference will now be recorded.
A very good morning to all. Am I audible? A very good morning to all. I am Sajid Kumar TS, Project Officer, Energy Efficient Building Cell at Energy Management Center. To keep the quality of sound functional during the meeting, please mute yourself when you are not sharing. Am I audible? Okay.
Yes,
we will turn the time over to ECBC trainer, Mr. Kumar Biplab. Over to you, sir.
Can you make me the presenter, please? Okay, very good morning, everybody. So today, what we are going to learn is how to model your baseline and proposed case for KS ECBC. And within baseline, I'm going to take specifically for chilled water buildings. Okay, so before that, let's talk a bit on the lighting. I think that's one section that we needed to do. So one of the requirements in KS ECBC is that wherever there are windows, you have to calculate the daylighted area, and within that daylighted area, all the light fixtures should have controls, as in dimmers or something like that. Now, specific clause. I'm going to show it here. When we come to the daylight section, this is lighting, yeah. So as you can see over here, under mandatory requirements, you have control in daylighted areas. So it says luminaires in daylighted areas greater than 25 square meters shall be equipped with either a manual or automatic device that is capable of reducing the light output of luminaires in daylighted area by at least 50% and controls only the luminaires located entirely within the daylighted area. So the next question that arises is, what is the daylighted area? So for that, you need to look up over here in the definitions, and here you have some called as the daylighted area. Now this is not so clearly visible, so let's take up the original ECBC. Okay, there you go. Right. So horizontal fenestration is specifically for skylights. So what it says that where you have a skylight on your roof, then edge on either side of the skylight will be your daylighted area, and if there is a ceiling height opaque partition, then that will not be considered as daylighted area. Right? And here are the different ways in which you can have the daylighted area. So this is the roof. This is a cross section, okay, and whatever is the height of the room, okay, that much on either side. Okay, so this is the plan. This is the cross section. And when it comes to something like this, then you'll have daylighted area as 2h, and this is where it's on sides. Over here it will be 1.5h. For vertical fenestrations, so this is plan view, and here is the window, and then 1 meter on either side or to the nearest opaque partition. So this is an opaque partition. Obviously this will not be daylighted. 1 meter over there, and I think this is 2 times the head height, or to the nearest 1.35 meters or higher opaque partition, whichever is less. Okay, so 2 times the head height. So head height, I'm not sure if it's given over here. So head height is just till the top of the window. Okay, so that's the head height, just till the top of the window. So that's head height, and that much will be the depth. 2 times the head height, 2 times the head height, and 1 meter. So let's look at our plan over here. And in this case, we had set the what was the cell level? If I switch on the layers, we have already defined the daylighted area. Okay, so let me see what is this distance. So this is 4.8, so 2.4 meter height, so 400. I think it was, I can't remember. So yeah, head height is 2.4 meter. Okay, from bottom of the floor plate till the head. So head of the window. So that's the head height, 2.4 meters, and twice that. Okay, so that's 4.8. And then if we look at here, this will be 1 meter, as you can see here. And this is 0.9 meter. So it says 1 meter or to the nearest opaque partition. So this is the nearest opaque partition, as you can see. Nearest opaque partition at 0.9 meter, and over here if we look, that's also 0.9, but on this side it is 1 meter on either side, right? So similarly over here, that's again 4.8. Okay, and nearest opaque partition, so that's 0.87. Okay. So any luminaires within this daylighted area will have to be controlled by either a manual or an automatic daylight sensor. Okay. Now, how do we model that over here? Let's say you have a window over here. Now, all you have to do is right click. Oops, sorry, I have to go to building shell. And oops, and you have something called as default daylighting. And you click on default daylighting and will calculate the daylighted area automatically. All right. Similarly, for here, and oops. So I'm right clicking and I'm clicking on default daylighting. Okay. For installing the daylight sensor, is there any dimension of position to be considered? In eQuest, no, not really. But specifically in the project itself, practically, that's for the lighting consultant to decide. You just have to tell them the daylighted area and you have to tell them that within this daylighted area, you have to control. Yeah, so if there is daylighted area, then yes, you have to probably position the windows correctly, but a bit here and there really does not matter too much because you have to understand you're comparing two cases, the baseline and proposed. Okay, so it really does not matter too much if because you have to model both in baseline as well as proposed. So if the sensor is modeled here in baseline, the window will be at the same position in the proposed case also, so it wouldn't really matter too much. Okay, don't there are two things you can you can sacrifice accuracy and time. You have to make a trade-off between accuracy and time. If you try to increase accuracy, you'll lose time. And accuracy, within 1%, as long as it is 1% accurate, I mean within 1% of control range, it's okay, doesn't matter too much. But trying to position the windows very accurately is going to cost you time, that's for sure. Okay, that's basically for daylighting. Okay, and you can actually go into that space, and if you double left click, you'll see under daylighting here the sensor location has been specified and how much is the controlled kilowatt fraction. So it says, so what this means is 49% is controlled by default. You can change this later on if you want. Okay, so that's basically regarding daylighting, and there's one more which is for occupancy sensors. Now occupancy sensors are also mandated As you can see, automatic lighting shut off. So for interior lighting systems in buildings larger than 500 square meters shall be equipped with automatic control device. Okay, and this, as you can see, this is occupancy sensors. If you have occupancy sensors, as per ASHRAE, because you have to understand KSEC or ECBC is taken from ASHRAE. So ASHRAE says that you can decrease your lighting power by 10% if you have occupancy sensors. And yes, we also have to look at the area. So as you can see, it is 23 square meters. What is the requirement? It says the luminaires in daylighted areas greater than 25 square meters. Only then you have to provide automatic controls. That's another thing that you have to remember. So in this case, technically, in this space, you don't have to provide daylight sensors. But over here, I think this is even less. So technically, you don't have to provide daylight sensors anywhere. Okay, I hope you're able to understand. This clearly says luminaires in daylighted areas greater than 25%. Okay, when we measure the area, it comes out less than 25 square meters. So no daylight sensors. Although I've shown it how you have to place the daylight sensors. But in reality, in this specific case, it's not required. Okay, so what is the minimum value of daylight pursuit after which lights shall turn on automatically? No, here you are not going for switch on or switch off. It is dimming. So as you can see, it is capable of reducing the light output. Okay, and that depends on the lux levels. Whatever the lux levels are required, you have to base it on that. Ideally, in eQuest, it says that under daylighting, you can see the set point is 50 foot candles. I think if you convert foot candles to lux, probably not very sure. The multiplying factor might be 10. I can't remember. Regarding the copy of the CPC document, I think you can ask the EEV cell. They should be able to share it with you. Yeah, dimming has to be coordinated by the sensor exactly, and yes, luminaires also shall be capable of dimming. So if the luminaire is not capable of dimming, obviously you can't dim the lights. Okay. So if I have to remove the daylight sensors from these areas, all I have to do is go to daylighting and say no, and that's it. So this will be removed. Go to spreadsheet view and daylighting, and wherever it is turned on, I can just switch it off. Okay, you can see everything is gone now. All right. That's that. Any other further doubts or clarifications on this before we proceed further? Okay, all right. Let's go to table 11. Yes, you can use LED patterns or tube lights for professional lighting. Absolutely, yes, you can. I mean, these days everything is LED, and yes, they are dimmable also. Okay, so give me 1 minute to look at something. Okay, if you have any doubts, you can probably ask while I look for a document.
Can I fill in between?
Yeah,
As Archana asked for the ECBC document, Archana, it is available on EMC website also, or you can else just type KSCBC 2017 in Google. You will be getting a PDF about it. Okay. Thank you.
okay, give me 1 more minute. So that's for the lighting designer to consider. You have to make sure that your minimum lux levels are maintained. Obviously, when you have taillight, the lux levels will be higher. Yes, absolutely. You can simulate with any type of window you want, any type of glass you want. It will automatically calculate the uh, amount of daylight that is coming in. Okay, I have found the document. Okay, so whenever we want to start a project, it's always ideal to actually prepare a comparison sheet. Okay, so whatever is given over here, you have to translate that into modeling inputs. So basically this is the input that will ultimately go into eQuest. Now let's look at, I'm going to cover the main points. So schedules, for example, the space use classification, it should be as per each space, and it should be the same in proposed building and standard design. So standard design is also called the baseline, and this is everything which is provided in ECDC. So standard design refers to the minimum requirements as per the ECDC standard, and proposed building is whatever you are building. Okay, so anything that is not yet designed or for which you do not know the specifications, for example lights, you can either take an assumption or you will keep it same as that of standard design. Okay, but obviously when you are going for a fit out, for example core and shell building, where you do not know what the tenants will install, you have two options. Either you can have uh, the client, that is the owner of the building, have an agreement wherein the lights that will be installed by the tenant will be so much wattages or so much lighting power density, or you have to model it same as baseline. So obviously if you say, or if you put it in the agreement, then obviously you can claim that credits. If you reduce the lighting power, obviously you will be ending up with lower energy consumption as compared to standard design. Okay, so that's one of the things. So we'll directly go to the schedules. You have to keep the same in both baseline and proposed case. Building envelope. Now building envelope, it says that so the left one, remember the left one is proposed case, the right one is baseline case. Okay, so let's go over the proposed case. So what the proposed case says, proposed case on the left, proposed case says that any envelope assembly that covers less than 5% of the total area assembly type, example exterior walls, need not be separately described. Okay, so what this specifically means that if you have columns and beams, you can actually ignore them, because that will form less than 5% of your total wall area or roof area. Okay, so columns and beams are ignored. Then okay, you can ignore what this means. Exterior surfaces, can leave that out, and yes, the manually operated fenestration devices are not modeled. You cannot take credit for manually operated lines or shades. Okay, only if there are permanent shading devices such as pins, overhangs, and light shelves can you take credit for that in the proposed case, whereas in base case will be without any shading devices. Okay, and one more thing is that orientation. So you have to rotate the orientation at the actual orientation, rotated by 90, 180, and 270 degrees at that, and then you have to simulate all the four and take the average. That will be your baseline case. Okay. Then opaque assemblies such as roof closed doors shall have the same heat capacity as the proposed design. Okay, but with the minimum U factor required in para 5.3.1 and para 5.3. So what this means is, let us say you have brick wall in your proposed case, then obviously you need to model in base case brick wall, but the U factor will be that of para 5.3.1 and 3.2. Okay. Obviously, we need to provide insulation also. Only then you will be able to match the requirements over here. So to give you an idea specific to that, let's look at this. Okay, so first is roof. Proposed case, we are saying 150 mm concrete slab with mortar on top and maybe tiles if you want to add. U value, we get it from eQuest. So what I've done is from eQuest, whatever values I'm getting, I'm either converting them into SI units. Okay, these are my units, as you can see. Okay, these are the units that are given in ECBC, and those are SI units. Whereas eQuest, it follows inch pound IP units. Okay. So roof 3.57 is the U value which we got after multiplying 5.678, which is the conversion factor for U value in eQuest. Okay. So that we saw yesterday. For example, over here we have proposed roof construction, and here is 0.629. Okay, so that's what we had got, 0.629. Then standard case, it clearly says that your U value, that is from table 5.3.1, that was specified here, para 5.3.1, which is for roof, it should be 0.409. So in eQuest, it should be 0.072. So obviously you have to give insulation, otherwise we just can't get this U value. So let's go ahead and create the baseline roof construction. So for that, I'll create layers, create will be baseline roof layers. I can copy it, and insulation, in this case, insulation has to be above deck. That's one of the requirements. So what we'll do is here we'll take in insulation. I'll put concrete here, and okay, this was CC4, okay, this one, and here from library I'll take insulation. Probably use poly. Of insulation, so polyurethane foam, maybe 5-inch. Let's see where it gets us. Now we have constructed the roof layers. We need to create what I would suggest is, in fact, just rename this as simple roof construction. Yesterday we had created, and this is wall construction. And have layers as either proposed wall layer or baseline wall layer. Okay, so that you can change anything you want. This will be proposed roof layers. So all you have to do, for example, just to check, is change this to baseline roof layers, and you got the calculated U value of 0.030. What we required was 0.072. That means we have to increase this U value, which translates into reducing the thickness of this. So although it says polyurethane 5-inch, you can just go to the material, make it, let's say, 4-inch, and reduce the thickness. So 4 would be 0.33 feet. Okay. See, the moment you change that, and you are going up to 0.038. So let's decrease it further. Maybe 2 inches. Okay, there you go. So 0.071. What we wanted was 0.072. So slight here and there, that's perfectly fine. To the question of Santi, what about a roof having an air cavity in the form of air sealing? Obviously, you can create false ceiling right over here. Okay, right in the layers, but obviously the values provided here are without the false ceiling. Okay, so make sure that you get the U values 0.071 over here first, and then you can include, if you want, your air cavities from here. So let's look at air layer and sealing airspace. Okay, and here you can have cluster ceiling tiles. Let's see if we have ceiling tiles somewhere over here. Okay, we have cluster somewhere. Gypsum. Okay, gypsum. I'll take gypsum for now. Okay, more or less similar. So 1/2 inch gypsum as the ceiling tiles. Okay, and you end up with 0.064. So really not too much of a problem, with when you include the air cavity. So doesn't decrease too much. But obviously you have to make sure that first you have your 0.071. Okay. So for now I'm going to remove this. Okay, so that we have 0.071. And I'll switch it back to proposed roof layers. Okay. Next would be, as you can see over here, is the roof reflectivity. The roof reflectivity, it says in baseline case should be 0.3, However, in equest, we enter absorbance, which is 1 minus reflectivity. Okay. So 1 minus 0.3 is 0.7. And in proposed case, if you are proposing high albedo paints, you can have that roof reflectivity as 0.95. If not, if you are not proposing high albedo paints, what KS ECBC says that it should be 0.45. That's 1 minus. Okay. Just need to recalculate the formulas here. Okay. So if you have high albedo paint, it will be 0.95, the roof reflectivity, or whatever the value is, the reflectance value is. If you don't have anything, it will be 0.45. Okay, that's what I'm not sure if it is written over here. Okay, for exterior roofs other than roofs, then the reflectance and emittance of the roof surface shall be modeled. The reflectance and emission tested. Okay, it doesn't specify very clearly, but if you look at ASHRAE, it will be 0.45. And as you can see over here in baseline, it says all roof surfaces shall be modeled with a reflectivity of 0.3. Okay, so that's about the roof. And let's look where we enter that. It's just right over here. You see absorbance. So this for the baseline case will be 0.7. Okay, had it been the proposed case, okay, here we have proposed case, so by default it will be 0.55. In proposed case, had it been baseline, it would have been 0.7. Okay, so for now let's keep it as proposed, and I'll say it as 0.5. Right. The next is wall construction. So let's look at wall construction over here. We're getting calculated U value of 0.373. So 0.373, which turns out to 2.12. In the baseline case, it says it should be 0.44 KSECBC. In IP units, it will be 0.077. So let's look at that. How do you want to create? Is I'm going to copy this. This will be baseline wall layers. Copy, and I'm going to add insulation here. We'll add maybe back insulation. Yeah, 19 plasterboard. Just use gypsum board for now. And obviously I have to change this to baseline wall layers, and we are getting calculated U value of 0.04, but we need 0.077. So obviously this needs to be reduced. I can go to material. So this is 0.511. It's almost 6.1 inches. Maybe I'll change this to 4" and change the thickness 0.333 feet. Let's look at this. Correct. And construction, I have baseline, I'm getting 0.061. So maybe I need to change this further to 3" and let's see 0.076. There you go. Okay. So that's my baseline wall layers, while my proposed wall layers is 0.373. All right. Let's save this. So that's the most of it of regarding envelope, and of course there will be the window. So maximum allowed window in standard case is 40%. If in the proposed case you have a window to wall ratio of, let's say, 55%, then in base case you have to model it as 40% only. So you basically reduce the height of the windows in base case such that you get the exact 40%. And how do you find out the window to wall ratio? You get it from LVD report that is generated by eQuest. Okay. So in fact, let's go ahead and simulate this for a minute. And we view the detailed simulation output file. And we go to LVD. Over here you see LVD. Okay. And then you need to scroll down. Okay, there you go. So that's, let me zoom this. Okay. So you have northeast, southeast, southwest, northwest, and roof, and then you have all walls. So we are looking at this. So in our current case, our window to wall ratio. So this is the window area, and this is window plus wall area. So it's less than 10%, as you can see. So this is 1242 square feet. This is 12501 square feet. So obviously, this is less than 40%. We don't have to worry so much. All right. And of course, the glass. So in ECBC, you get the SHGC, which is 0.25. Now, where is that? Okay, so they have not specifically given the table number, but you can just look up here in envelope section. There you go. So in the baseline, the first thing, window to wall ratio, if it is between 0 and 0.3, you need to have 0.27 VLT, and your U factor will be 3.3. Since your window to wall ratio is less than 40%, your maximum SHGC will be 0.25. Okay. So 0.25 will be your SHGC. In eQuest, you have to enter shading coefficient. You divide the SHGC by 0.86 and you get the shading coefficient. and then new value. And I think one thing I missed over here is the BLT. BLT is required if you are inputting daylight sensors, otherwise it's irrelevant. Okay, so in the base case, no, you can. It's actually much easier to reduce the size of the existing windows that you have than inputting it at different locations. Everything, if you put it throughout all the spaces, 40% throughout that stuff. Although if you look at the code language, it says that you should distribute it everywhere on all facades, but that's just impractical. And um, this is based on ASHRAE 2004, and after that this has been removed. So you can just, as you can see here, fenestration shall be distributed uniformly in horizontal bands across the four orientations. That's just, you have to go back to wizard mode and recreate everything from scratch. That's just impractical. So just ignore this line, and wherever the windows are, reduce the height to make it 40%. Okay, and the reason being that this language has been removed from subsequent revisions. Okay, that's that. Give me 1 minute. Sorry, just 1 minute. Any questions? If you have any questions, please feel free to ask. Give me 1 minute till then. Okay. So that's about the envelope. And then next we will be going for lighting. Okay. Yeah, one more thing is the frame width and shading depth. So in frame width, in proposed case, it will be as per actual. In standard case, it should be 0. So here, if you click on any window, you will see this frame width. It should be set to 0 in this case. Okay. And obviously, no shading allowed in baseline case. Next, we go to lighting. Okay, so when it comes to lighting, it just says either you follow building area method or space by space method. Now, most of the time, it's quite easy to follow the building area method so that you can quickly do it for all the spaces. But if you want to do it space by space, that's your call. But space by space method, it takes time. You have to look for each space and find out the LPD for each space. Whereas here, it's just simple. And of course, if there are any occupancy sensors, you need to take that into consideration. As you can see over here, lighting controls shall be the minimum required. So for I'm going to split this. Okay, we are in lighting. Lighting control shall be the minimum required. So let's look at for a school building, what is the LPD provided. Okay, so this is building area method for a school building. It is 12.9. Okay, and of course you have to provide uh, automatic shut off, that is the occupancy sensors. So what we'll do is, so 12.9 is the baseline LPD, and we'll subtract 10% for occupancy sensors. So it'll come out to 11.61. In proposed case, whatever, if we say we are going to about 0.5 watt per square feet, it turns out to 5.38 watt per square meter. So if I'm going to input 1.008 into equest, all I have to do is go into internal loads, go to the spreadsheet view, go to lighting tab, and just enter 1.08. And that's it. Okay. And if I have to do, or if I have to change it for proposed case, again, we'll just make another file and then we'll change it. Okay. That's about lighting and daylight sensors. Obviously, as you can see, as per 8.2.1.3, required if daylighted area greater than 25 square meter. So we say that this is no. And whatever equipment power density you have taken, you can either assume it or as per actuals. It's very hard to get actuals. So school building, okay, 0.25 watt per square feet is okay. If it's an office building, maybe 1 watt per square feet. So that's something that you can enter over here under equipment. Okay. So that's basically it regarding the basic items: envelope, lighting, equipment. So those are your loads. Okay. Infiltration, It is as it is. Next is HVAC system. Okay. Now I'm going to probably do two things. One is I'm going to show for VRF unit. The other is with chilled water unit. So first I will start with chilled water units, and then probably in the second half, in the second session, we'll look at the VRF unit. Okay. So standard case, how do we decipher what should be there in standard case? Let's look at that first. Let me remove this split view. Okay. So whatever is written here, I've just translated it for you into a simple Excel file over here. So you don't have to worry too much. Okay, so this is the system map. Based on your area, you have to select the baseline system. Ignore this residential. Obviously, yes, ECBC is not for residential, but residential can be considered, for example, in cases of hotels. In cases of hotels, it will be the residential system in the baseline case. Okay, for the dormitories, sorry, for the rooms. Now, focus only on these wordings: less than 3 floors or less than 7,500 square meter, or more than 5 floors or more than 15,000 square meters. Focus on these two wordings. Just ignore whatever is written in between over here, because it is just too messy. So less than 3 floors or less than 7,500 square meter. It says that you go for packaged rooftop air conditioner with constant volume. The cooling type should be direct expansion and heating type should be electric resistance. Okay. So hot, and obviously in this case, each zone will have its own system. Okay. So that translates into that every system will have only one zone attached. Okay, and this clearly says that it should be packaged rooftop air conditioning with, that is basically direct expansion, so which is PSZ, stands for package single zone. So you have package single zone, as you can see, DX and electric. In the background, if you can see, DX cooling coil and electric coil as heating. Fans, if you come here, it says it should be constant volume. Fan control is constant volume. Cooling type direct expansion, heating type electric resistance. The only thing that it says that each system should have only one thermozone. Okay, so for that, all we need to do is create another HVAC system, copy, and we'll just, for example, classroom 3, we'll put it in here. Okay, in a similar fashion, we'll create for each of the classroom. Okay, and if it is these other two buildings, it will be central plant with AHU for each zone. Okay, I do not know what they were thinking when they write AHU for each zone. That basically translates for, this is what we have. Each zone will have its own system. I don't know why they wrote it, but in these two cases, it should be per flow basis. I'm pretty sure this is wrong. We can actually check with what is written over here, the main ECBC. Here also they have written for each one. Okay. Okay. So this unfortunately should be for each floor. We can actually look at the guide that comes with it. Give me 1 minute. I'll pull up the exact wording. So this is the user guide that was provided earlier. Let's actually see. Now, as far as I remember, it should be per floor and not per zone. Let's see. Okay. So, model these, entire floor into one single AHU. That's what we had here. Just ignore these wordings. So basically, it will translate into over here, and we'll delete this. So this is what it refers each floor. So in fact, even this lab 1 will also go into here. Lab 2 will also go in here. This will go here. Okay. So this is the configuration that you are looking at. One AHU per floor. This is a system that you are looking at when you model either of these two. So this is only applicable if it is, greater than 3 floors or greater than 7,500 square meters. All right. Greater than 3 floors or greater than 7,500 square meters. So let us assume for a moment that in our case, although we built only 2 floors, I'm going to give floor could have created one more floors here. Let's just give it a floor multiplier, the ground floor maybe 5. Okay, so What this means is there are 5 floors of this and 1 floor of this, the top floor, right? So 6 floors overall. So let's assume there are 6 floors. So for each floor, we'll have one AHU, and here it says central cooling plant with constant volume AHU, and this will be variable volume. Okay, just ignore what is written over here. So we have our chiller. All we need to do is change this to variable air volume. Select the CSW loop. Obviously, it will be always the secondary CSW loop. Done. And this will be variable air volume. CSW loop will be secondary CSW loop, and done. Why is it still show? Heating will be by electric. That's it. Okay, the heating will be electric and chilled water files. Okay. The only difference between this and this system is that one is constant air volume, the other is variable air volume. So all you have to do here is under fans, one will be constant volume or variable speed. That's it. You'll either specify constant volume or variable speed, depending on which type of system it is. So had it been five floors, I would have selected constant volume. In our case, it is 6 floors, so I'll select variable speed. Oops. Right. Here, variable speed. And that's about it. Okay, there's one thing that I'm bringing in here. Is basically this fan curve. Nobody asks, unfortunately, nobody has shown or nobody gives over here. But if you do higher level modeling, then you also need to give the fan curve. For now, you can just leave it at constant volume or variable speed. That's perfectly fine. Okay, don't need to give the fan curve. Just variable speed or constant volume will be sufficient. All right. So is this clear? Like till here, till the HVAC system, how we model the HVAC system for the baseline case. Of course, there are some more inputs that we need to give specifically with respect to the fan power. Okay, what should be the fan power in the base case? That is the question that I'll be answering shortly.
Sir, you just showed for the default value. If it is not a default value and we are doing a higher model, what should be done there? Fan EAR equal to?
Select this fan EIR FPLR, and from library select AHU fan power, and here is fan power FPLR with VFT. So
Okay.
And you can actually modify these curves if you want. Obviously, getting the data is just, you don't get it from the manufacturer. See here, you can modify these values if you want. Yeah, or you can use raw data points to get a curve. Okay, but I would suggest not going into all those depths, sticking just to.
Will that provide any drastic change to the model value?
Sorry, could you repeat that?
I mean, if I didn't do that and just use the default value, will it provide a drastic variation in my API?
No, no, no. It won't result in a drastic variation.
So I can, okay, so it is better for a default.
Yeah, you can go for default. Yeah. Okay, but for other people, I think just variable speed or constant volume is sufficient. Okay, that's that. Okay. Now, this is okay. In baseline, everything should be at default. And one more thing that is required is the oversizing, which is specified here. So oversizing, the pool sizing ratio in the baseline should be 1.15. Now, if you look at the air handler over here, okay, the sizing ratio. Here you can keep the sizing ratio as 1 and go to cooling, and you can increase this pool sizing ratio to 1.15. Okay, if you are doing the baseline. And in heating, you can make it 1.25. Obviously, our heating will not be switched on because of the uh, way we have put these thermostat schedules. So obviously the heating will not be switched on, even though the design will be done for 72, but the heating will never get switched on. Okay, that's number 1. And one more thing is treated fresh air unit. I think that also you need to give specifically, even in sometimes in chilled water units, they give TFA units, treated pressure or dedicated outdoor air units. And sometimes, and in fact in VRF it is very much required because you have to give the pressure. So what would you do in those cases? So what is happening is the pressure is being drawn from a separate unit, which is called a TFA unit. So what we'll do in that case is we'll create another system downstream. We'll transfer all of these zones to that system, and then air will be drawn, the fresh air will be drawn from this system. To do that, we need to create a dummy zone. Okay, let's first create another HVAC system, which is similar to this. All right. And then let's transfer all of these to the new system. Okay. So now this will be our TFA unit. So what I'll say is, let's say these two systems, this and HVAC system. Let's call this HVAC sys 1 and let's call this as 2. Okay, so both of them will drop the outdoor air from TFA unit. So as you can see, outdoor air from system, here you'll specify TFA unit, and here TFA unit. Now, because this is a conditioned system, okay, you need to have a thermal zone in here. So what we'll do is, in building shell, we'll create one thermal zone. Okay, create from scratch, no shape. We'll say this is 1 feet by 1 feet. So this is like a, I'll call this as TFA space, TFA dummy space with no equipment, no infiltration, no daylighting, nothing, no internal loads. There's no internal loads in this. This is just a dummy space. And correspondingly, I have to create another zone. So create a thermal zone. I'll call this as TFA ZN. And the parent system will be TFA unit. You can copy an existing component, click on OK, and here you have to select the space, and that should be it. Okay, and you can specify whatever is the total outdoor air, you can specify in here, but it will automatically draw whatever air is required in the zone. Obviously, no minimum, since there are no people, obviously nothing will be drawn. This is all okay. Yeah, so leave everything blank. So what will happen is, whatever air required downstream by these spaces will be drawn from the TFA unit. Okay, so please remember, the TFA unit should be at the top of it. Only then the bottom ones can draw the air from them. Okay, so we can do a test simulation for now. If there had been a problem, obviously the simulation will not run. Okay. And you can look at it in SVA, system design parameters. So as you can see, the cooling capacity, it says it is 488 CFM. I mean the supply CFM, it is saying 488 CFM. And that 488 CFM is a byproduct of over here, from here. So TFA unit, let's say HVAC system 1, the capacity is 5923 CFM, but as you can see, the outside air ratio is 0.026. Okay, and you can actually calculate 5,000 here, 5,000 into 0.26. So that's 130 CFM here. And 21141 into 0.079. Okay, so obviously there is a bit of mismatch. This is 130 and this is 1670. So it should have been really, even higher. So let's look at, did we specify for the second one that it will draw from TFA unit? Yeah, it will. I think this is, I missed one here. Ideally, it should have come. Maybe I'll just take a look. So here you can also click on summary. After you simulate, you can also click on summary to get the details in a concise manner over here. So ideally, this should not have been 488. It should have been higher. That is the sum of, as you can see over here, the outside supply air is 153 here and 1673 here. So obviously, it should have been sum of both. And you can say the minimum flow is 100%. So I probably just need to take a look as to why that is not happening. But ideally, it should have happened. And all right, sorry. Yeah, I missed here. Where this should have been 1. Minimum outdoors outside air ratio is 1. I think now this should ideally be solved. Look at summary. No, it's still not being solved. Okay, ideally, this is how it should be. I probably just need to take a look. Maybe I can, in the second half, I can just tell you why or how we can exactly do that. Okay, for now, this is how you have to build the TFA unit, and outdoor air should be from the TFA unit. Right. That's that. Any other thing that I need to cover? Okay. Yes, one of the next important things is basically your unmet hours, right? So remember, we were talking about the unmet hours yesterday. So as you can see, this is called the unmet hours. That is, our temperature is not satisfied. You can see here it is 173 hours. Now, as per rule, as per the law, it says that both baseline and proposed case should not exceed 300. Okay, and the difference between baseline and proposed should not exceed 50. Okay, it can be plus or minus 50. The first is it should not exceed 300 in either case, and proposed minus baseline should be within plus or minus 50. So this is what it means. You have 173 hours, which is less than 300. So we are all right here. Okay, that's that. And you have to also give the system COP. Now, in case of chiller based systems, we have to give the COP here. For that, we need to find out the capacity of the chiller. Now understand that this was all on auto size. In fact, let's first check whether we have baseline. We have the construction should be for the baseline. Okay, so this is baseline wall layers, and the roof construction here will do it for the baseline roof layers. Okay, then of course your class, you can change that over here. The shading coefficient should be 0.29 and be 0.581. The conductance VLT is 0.27. So this is your glass, right? Then internal loads in lighting, we have already set it. The LPD is correct. In the air side, we have set variable air volume, and the fans, this should be variable speed. Yes, because we have considered 6 floors. This is variable speed. Okay. And one more thing, as I was telling you yesterday, the temperature difference between supply air and the space air should be 20 °F. So let's just look at that. Yeah, here. So our space is set at 78.8, if I remember correctly. Let's look at it. In the cool weekday, it's 78.8. So here under cooling, this should be 58.8, right? And same goes for here also. Okay, that's one of the rules. It's not listed here, but I'm telling you, this is in the detailed guide, which you can always refer, the UCBC detailed guide. That's that. And then of course the chiller efficiency. So here the chiller efficiency, will find out the chiller efficiency in a moment, because that depends on the capacity. Okay, as you can see in easy over here, under HVAC, see, for different types of chiller, they have given different types of COP. Now what should you take? What should be the baseline type? It clearly says it should be, it's given in the ECBC user guide. It says less than 300 tons, so it should be 1 water cooled centrifugal chiller. If it is between 300 and 600 tons, it should be 2 water cooled centrifugal chillers sized equally. If it's greater than 600, then 1 or more chillers each of 600 tons or less. Okay, so where do we find the capacity? In fact, we should resimulate because we made the changes here. Okay. The capacity is found in, yes, now we have 1796 throttling hours. Okay, so that means increasing the insulation is actually detrimental. If you have a high heat load, it's trapping the heat inside. And in fact, let's look at which zone we have throttling. First, we need to eliminate throttle, then we can go for so we have almost all the zones in HVAC system 1 and system 2 which are having throttling. Now this, the reason being that we changed number one we changed the glass, and number two we changed the wall, I'm sorry, roof. So those two construction layers. Okay, yeah, roof construction is baseline roof layers and wall construction is baseline wall layers. So what is happening is basically, because this building really is very small, it is trapping all the heat that is generated within the space. So how do we eliminate it? So one of the first few things that we will check is we'll go to SVA report and we'll see how it is, how is the sizing. Okay. So you have a floor area of 25,000 square feet and a capacity of 15,366. So you can probably increase this, right? You can increase the supply CFM so as to eliminate the throttle range. So this is less than 1 CFM per square feet. Ideally, it can range from anywhere from 1 CFM to 2 CFM per square feet. So you can probably take that a notch higher. In the proposed case, for that you need to go to the zone and you need to go to airflow. As you can see over here, the minimum airflow per area it is specified is 0.5. You can increase this to probably around 1. Okay, I'll increase this almost everywhere because if I see HVAC system 1 also, I'm going to end up with the same. As you can see, it's less than 0.5. Right. So this is one of the ways you can decrease the throttle range or the unmet hours. As you can see, the capacity it has matched. And now if we go to SSR and let's see, okay, as you can see it has decreased, but there's still one zone which is at a higher, and here everything has decreased. Okay. So maybe this 354, this is L1 classroom 1, we can slightly increase it, maybe 1.1, and I think that should eliminate all the. So this you can do it in baseline. In proposed case, you have to obviously have the actual. As you can see, it has reduced to 112. The number of unmet hours are under full. And if we look at BPU report, you can see it is 189. All right. Now, once this is controlled, the other thing that you need to give is the fan power of the supply air fan. Okay. And then finally, after we give the supply air fan power, we will find out the capacity of the tonnage. Okay. So here, for the supply fan power for the baseline, we'll refer the national ECBC 2017. So here also we have everything listed. So as you can see, fan power, it says that CMH into 0.51. Okay, just multiply the cubic meter per hour by 0.51. So the approximate cubic meter per hour, here we have CFM. You can go to, from here itself, click on summary, click on the project itself, and in here we have 5077 CFM. CFM to CMH. So 5077. In fact, let's just this one. So 1 CFM is 1.699. So what I can do is here H1 CFM and CMH fan power in and fan power for equest. This is something that you can quickly create. So CMH is this into 1.699, and the fan power says that you multiply the CMH by 0.51. This will be in kilowatt, and for equest you need to enter kilowatt per CFM, which is this. This is kilowatt and this is the CFM, right? So for AHU1, what we got was 5077. So I'll just enter 5077 here, recalculate, and that's my, oops, sorry, this is in watts. I have to divide by 1000. Yeah. Okay. You're probably going to end up with the same for every system. AHU2, we had got 25091. 25091. Spreadsheet, and as you can see, it is all the same. Okay, 0.00087. So all I'm going to do is go back here in the spreadsheet, go to fan power, and just copy and paste this value. Okay. And now all I have to do is simulate. Make sure I have the throttle range within control, less than 300. And now I have to check the capacity. So that I will check from PVA, which stands for plant design parameters. So here you can see the chiller. Okay, had we entered the rated capacity here? Just check that. Oh, I'm so sorry. This should have not been there. How do we remove that? This should have been a centrifugal. One second. So, okay, because we had entered 2 MBTU per hour, which should ideally not have been, because this should be auto-sized. I'm probably just going to create another chiller. Chiller 2, chiller type, say, centrifugal. Let's see if I can make this as 5. I'm not very sure why this is taking 0, but this should ideally be blank. So if you have 2 chillers, you can give capacity ratio of 0.5 and 0.5 to both the chillers, so they will be sized equally when they are running. The only way that I can think of is, edit this file in the background. We have actually a code called inp file, which is just like a text file, as you can see over here. You can probably study the inp file more if you want. So all I'm going to do is go to the chiller section here and remove this capacity line, save this, and reopen this project. Hopefully that should. It always asks for capacity. That's strange. This is a bit strange because ideally it should not be asking. Okay. Let's see if I set it to blank. Okay, let's see what happens if we set it to 0. You can also try that out. I'm sure it will run into an error. So this is a bit of trial and error with an understanding of what you're trying to do. Okay. It ran the simulation and did it give us capacity? Yeah, it gave us the capacity. So just enter 0 and run it, and this is what it should have been. It automatically takes that. Chiller 1 capacity is 0.568. That's what it has come out to be. So you convert. Ideally, initially we should have had just 1 chiller. So I'll delete chiller 2 and resimulate it here. Let's see. Okay. So we got 1.135 as the capacity for this building. So in terms of terms or tons, see where it says If it is less than 300 tons, it should be 1 water cooled. If it is greater than 600, minimum 2 chillers. So let's see how much it is. So 1135 divided by 12. So that's 94 tons. So just one chiller is sufficient. Okay, I just converted the MBTU per hour into tons. You can do that in your online conversion also. Just Google search MBTU per to tons. Okay. So you can see 1 MBTU is 83.33, and what we had got was 1.135. So 1.135 times 83.33, you get the same 94 tons, 94.58. Okay, and you look at the PU report. So this, with this, you complete the baseline for a chilled water plant using a chilled water plant. Okay, I hope this would have given you an idea of how to also fix things when you get throttle range and where to find what. So any questions here? And I think in the second half, we'll look at the proposed design and also VRF systems. If you have any questions, please feel free to ask.
Participant, you can unmute yourself and ask questions. It's the time. So I think we can take a break now then. Okay, there's a question.
Why TFA is created? So if you have a TFA unit, obviously you need to create a space. You can do a trial and error, and you will see that if you run uh, any system without a corresponding zone, conditioned zone, Equest will not run. It will give you an error. So that is why TFA is created and a separate. Okay.
Anyone else?
Okay. Sorry, I said that you have to run. Every system needs to have a conditioned zone. Now, TFA unit, if you have to model it separately, because obviously a TFA unit will consume energy, treated pressure units, and that needs to be modeled, not in the baseline per se, but in the proposed case. When you have a TFA unit, you need to model it explicitly. In this case, I was just showing it, but you can actually delete it off if it is a baseline case. Every system needs a condition zone, and that is why we need to create a null space so that a TFA unit can be simulated. And if you do not want to do that, then probably you just have to add the fan power of the TFA unit also in your proposed case. If you don't want to model the TFA unit, just make sure that you add the fan power to the proposed case.
So, sir, we can take a lunch break now, I think.
Yeah, absolutely. So
Okay.
we'll reconvene at 2.
So we can gather by 2:10 and we can resume by 2:15. I think people they will be entering by one-on-one.
Okay,
So
sure.
the participant be ready by 2:15. We will start the session. Okay. Thank you, sir.
Okay, right. Thank you.
Yes, sir. Okay.